I'll talk about error analysis in this lecture. Suppose you are measuring the sides of a notebook you may have. Let's call one side as x plus minus delta x. And suppose you measured that side, let's be it this one, to be 29.4 with plus minus with error 0.1 centimeters. Okay, so this is one side, and the other side, let's name it as y, together with its error delta y. And let's measure this to be, suppose, 41.3 plus minus, and with an error of 0.2 centimeters. Okay, it can be this side and this side. So, there are, of course, reasons for doing this. We might want to just to calculate the circumference of the notebook or the area, etc. So I will just define, in the first place, that whenever you do a measurement in physics, whenever you measure a physical quantity, you put what you measured. This is the measured part. This is the measurement. Okay, the first part. And you have to also record the uncertainty in your measurement. And this part is called the absolute error, or uncertainty, absolute uncertainty. Okay. We will also define this quantity delta x divided by x, the error over one measurement divided by the measurement itself. It's called relative error or relative uncertainty. Okay. You can just right away calculate, for example, for this is 0.1 divided by 29.4. It is dimensionless quantity because you divide length by divide, so you have no dimension. Let's do it. Let me just. Okay, so let's divide this 0.1 by 29.4. It is up to third digits after the decimal point is 0.003. Okay, so this is the relative error, and if you multiply this by 100, delta x divided by x, if you multiply the relative error by 100, in that case you just get the percentage error. Okay, let's define this as percentage error. Okay, so obviously it's going to be just multiply this by 100, you get 0.3. That means you get 0.3% error in your measurement. Okay, so you can do these calculations for every measurement. I just have done this for as an example for this one. So suppose next is you want to add these two measurements, right? They are length measurements, and suppose you define a quantity, let's say C, and you just want to add x and y. Okay, these two measurements. So you can just simply do this addition. It's going to be just 70.7 centimeters. But the thing is, the question is, okay, this is the result for addition, but what about the error in the result? What about the error in your addition? Okay, so one way is to have an idea of a possible result is that you might add, since the minimum measurement for this x measurement could be 29.3 because there is 0.1 centimeters of error. So you can use just the 29.3, and this is 41.1. Add these two, which makes the minimum value for C is going to be, let's put the C min, is going to be just 70.4. And similarly, if you just use the maximum values for x and y, you could have a maximum value for C to be so in that case, this is going to be 29.5 and this is going to be 20, so 41.5. It is going to be just 71, right? So this is a possible minimum, okay, minimum value for the addition, and this is the possible maximum value. For, you can take the difference, delta C, to be the difference between minimum and maximum value. Well, it's going to be like, in that case, 0.6, right, centimeters. So you can just put this delta C to be like 0.6 centimeters. So you can record C plus minus delta C to be 70.7 plus minus 0.6. But the 0.6 is large. I mean, most probably the error in your result is going to be less than the 0.6. This is the maximum value. Well, for addition of terms, for addition of measurements, we use a statistical average of these for this error, and that is to be calculated by using this formula, delta C. If we have delta X and delta Y in the first place in your measurement, delta C is going to be calculated by squaring delta X and adding to this delta Y square and take the square root of it. Okay, so this is the way, in the standard way of calculating the error for addition of measurement values and reporting the error value as like the result of this. So if you do this, 0.01 plus 0.04 and take the square root, so square root of 0.05. Let's do this also in your calculator. So when just take the 0.05 square root, we have lots of bunch of numbers, 0. After the decimal point, 0.223 606 and 7977. It goes like a train. Okay, so we have many digits. So should we keep these all digits and put this value over here as whatever you see as it appears on your calculator? Of course not. You cannot just simply put over here 0.20236, etc. It goes like crazy. Okay, so the rule says that, okay, you just look at your result. Okay, your result have only one digit after the decimal point, so the error part must have only one digit after the decimal point. This is the rule. If you just find what the measurement calculated measurement value, and just look at the number of digits after the decimal point, and the rule says that error part must have the same number of digits after the decimal point, which is going to be 1. So you must all truncate all of these figures, throw away, and put this as 0.2. Okay, so you see this result in your calculated error value is somewhere between this one and this one. Well, it's equal to this one in our case, but it cannot be larger than this one. It cannot be smaller than this one, obviously, for if you just think about it logically. But it's going to be just somewhere. Anyway, so well, what if you had, well, we had 2, 3, etc. Well, we just round this number until you have one digit after the decimal point. But while rounding, you know also how to round the numbers off, and just to make you remember, you just look at the number, just the second digit after the decimal point. If the second digit after the decimal point is the number like less than 5, then just throw this number and keep this number on not changed. Okay, it's the same. But if this number could be like maybe 6 or something larger, 5 or 6, something larger, and you throw this, but it will raise the first digit after the decimal point by 1. Okay, so keep this in mind. I hope that you know how to make the rounding digits anyway, but just to remind you how to do it. Okay, so all right, so that's it. But the other thing is that you might have one thing is that you might have, we're only talking about the addition. Well, this is a particular operation for using the measurement values, but if you really want to calculate the let's say the circumference of your notebook, okay, you just multiply this addition by 2, right? If you're talking about circumference, in that case your error will be just multiplied by 2, okay? So you just get 4 over here. If you're talking about the circumference, it's something else, not only just x plus y, but 2 times x plus y. So in that case, the error also will be modified, and with that same factor, you just put that factor over here. Okay, so what next? Well, you might ask, why do we use such a formula? I will talk about this later. This is something related with the statistical averaging of these addition of errors, etc. I will talk about this later maybe, but for the time being, just keep this as it is, okay? So next thing is that, okay, when you look at, okay, let's change the second measurement value, y plus minus delta y, a little bit. Let's make this 41.34, okay, plus minus, let's say 0.01 centimeters. Suppose you had used another measuring tool, which is more sensitive, obviously, than a millimetric ruler that can measure just the 1/10 of a millimeter. It has the smallest division as 1/10 of a millimeter or 0.1 millimeter on it. So you can just measure the second side as like this. Remember, we had measured this by using a regular millimetric ruler. It was 41.3, but now with this more sensitive device, you know now what the second digit after the decimal point. Over here, you're not sure about the second digit after the decimal. You only are certain about the first digit because of your device, you're using millimetric ruler. But over here, if your ruler is just showing 1/10 of a millimeter, then this is what you get, okay? So that means you're sure about the second digit after the decimal point. But the thing is, up to only one digit after the decimal point, these two numbers are just the same, we say. These two numbers are just the same up to only one digit after the decimal point, okay? Well, of course, arithmetically they're not the same, but in terms of measurements and in terms of the sensitivity after, let's say, in terms of the sensitivity up to millimeter, then these two measurements are just the same. Okay. In fact, it's not. Well, why? Because this is more sensitive. You see, this sensitivity or precision of your measurement improves when you use more digits, right? So there comes playing with these, the subject which is called significant figures. What are significant figures? Significant figures. Figures means numbers, just digits. In place of figure numbers or digits, you just use the term figure. And significant is just the word, significant. It has some important. Well, what are significant figures? Significant figures, first of all, for if you have a measurement result which has some decimal point, and if your result is not starting with 0, some measurements could be like 0.1, 0.25, etc. Well, in our case, it's not starting. Its leading digit is not 0. If your leading digit is not 0, we count all digits as significant. Okay? So the first rule about determining the number of significant figures in a measurement value, and I'm talking about the measurement value, not about the error part. There is no way to find the significant number of significant figures in an error part. There is no concept like this. We only define the number of significant figures for measurement parts, for measured parts. So, for example, this one has 1, 2, 3, 4 significant figures. Okay, 4 sig fig. But over here, this one has only 3 sig figs, right? and also this one x has three sig figs. This result is three sig fig, and this one is four sig figures. So as you can logically take this as when the number of significant figures is large or increasing, it's kind of your precision in your measurement is increasing, because you have more numbers. That means more knowledge about your measurement. So yeah, obviously it's going to be more significant. When you get the more significant figures, you get more precise measure. Okay, so this was the first rule. Well, what about if you're measuring part starts with a leading zero? It starts with 0 point, let's 0, 2, 0, 5, 6, 3, 0, let's say, seconds or kilograms. Okay, so in case you have such a measured value, it's again a decimal point. It has a decimal point, decimal value, decimal number. Well, the rule says if your measurement starts with some leading zeros, for example, the first digit over here is 0, and the next one is also 0. All leading zeros will not be counted as significant. Okay? So we're not counting these zeros as significant figures, but starting with the first non-zero digits, all digits coming after this, all to be counted as significant. For example, this is 0, not significant, this is 0, not significant. 2, it's non-zero number digit, so we start counting from by with 2. 1, next digit is 0, but since it comes after a non-zero digit, it is counted as significant. 2, 3, 4, 5, 6. The last digit is also 0, but we all count all zeros after non-zero digit as significant. So 1, 2, 3, 4, 5, 6. This has 6 sig fig. Okay. So this is the second rule about finding the number of significant figures. If your measured value starts with a 0 digit and continues with this 0 until a non-zero digit, all these zeros will not be counted as significant. Okay, so, and if you add more zeros over here to the end, you just keep increasing the number of significant figures according to the rule. Okay, so since I just added 3 more, this will make my result as 9 significant figures. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, well, adding all these zeros will not change the measured value. Obviously, arithmetically it's just the same with the one that without these zeros or zeros, but the number of the significant figures changing. We are doing something which is important, which is significant, by adding these zeros. Why? Because we are just giving this information that I'm sure about these digits. Well, when there is no zeros over here, I don't know whether the digits after coming 3 are zeros or not. I don't know. I don't have the knowledge. But by putting the zeros over here, that means, I can measure up to this digit, up to this and this, until this digit. So I can measure it, and I'm sure that these are 0. Okay? So there is a difference between this number and the measurement value without zeros. And this is lying with the just counting the number of significant figures. The without zeros, before it has only 1, 2, 3, 4, 5 significant figures, but if you add zeros over, you just increase this to 9 significant figures, saying that okay, this measurement result with more number of significant figures is a more precise one. Okay. All right. So what else? Well, I think this is all about determining the number of significant figures for a measured value which has some decimal point. What about exact numbers? For example, you might have like 1,500 kilograms as just measuring the mass of, let's say, a truck, etc., or a car. So how many significant figures in this measurement? If your measurement is an exact number, like 1500, or let's say 105, let's say kilograms, or let's say 23 kilometers, etc. These are all exact numbers. Are we counting zeros as significance, or something else? Well, I can say that for measured values which are exact numbers, finding the number of significant figures is not very certain. I can say it's ambiguous. Okay, it's ambiguous. So one way is that can we convert these exact measurement values into uh, decimal points? Can we do it? Well, answer is yes, of course. I can write this number as a number with a decimal point. Why not? Because let's see this 1.500 times 10 to 3 kilograms. You see, this writing is exactly equivalent to 1500, but the thing is, I just used this scientific notation, so-called the scientific notation, to report this measurement of mass like this one. So what is a scientific notation? Let me put it over here, scientific notation. Scientific notation is a way of putting your measurement values into a format which has the number part and the power part. So this is the power part and this is the number part. Number part is a digit, is a number between 1 and 10. So let's write this as x. This number part must be larger than 1. Okay, it can be equal to 1, but smaller than 10. 10 is not included. Okay, so the rule says that if you are converting a measurement, exact measure, or it may be also a decimal point, you might want to put in the scientific notation. It's okay also. But if you have an exact measurement value and you want to put it to a decimal number, then this is only the way to convert your measurement value into scientific notation. And while you are doing this, the number part must be a number between 1 is included, and 10, when 10 is not included, you cannot put 10 over here, but you can put 1 over here, times some power of 10. Okay, but so how to determine the number of significant figures in a scientific notation? We only look at the number part. We all count the number of digits in the number part to be significant. Okay, so 1, this is 1, this is 5, this is 0, this is 0. All these digits are to be counted as significant figures in the number part in scientific notation. So there is no any other exception. Just count all the digits as significant. So this has, in that case, 4 sig figs, right? This writing of 1500 kilograms to be 1.500 times 10 to 3 kilogram means that your your measurement has 4 significant figures. But well, you might also thinking that okay, so if you think that there should be only 3 significant figures in this measurement, then just you get rid of this 0, and that is 1.50 times 10 to the power 3. So you can always change the number of digits, number of significant figures, by just using this scientific notation. And let's do this. 105 kilogram. So if you want this to be 3 significant figures, one way is that 105 times 10 to 2 kilograms. Okay, so in that case you have 3 significant figures. 23 kilometers, 2.3 times 10 kilometers. So you have 2 significant figures. So because if you just report this measurement as 23, you're not sure about whether this 3 will be counted as significant or not. So the best way is just the this one. Okay, so you know now how to determine the number of significant figures, but next thing is that, I already done this addition. Well, this is going to be, of course, if you multiply by 2, but let's now go back to the original, just we add them. When you add two measured values, well, in our case, in our example, this were just like the same number of significant figures, both in x and y measurements. But what if you have different number of significant figures and you want to add them? All right. Okay, so in that case, we know we have to also, obey some rules of adding, addition of significant figures. Also, we will do some multiplication and other operations. Addition or subtraction, it has the same rules. And for multiplication or division, it has the different rules. But multiplication and division is the same, and addition and subtraction is the same. So suppose you just measured y to be not 41.3 but 41.34. And let's change this to be 0.01. So in that case, how are you going to report this summation? Well, again, let's see, is x plus y. We just add 41.34 with 29.4. You add these two numbers, okay? So just do your regular addition. 4, 7, and 7. 7.74 centimeters. Okay. Should you keep the result as this one? So the rule says when you are doing addition, or also subtraction is going to be the same rule. What you're looking at is that find the number of digits after the decimal point for each additives. This is the first additive, this is the second additive, and after the decimal point we have on the first one 2 digits, and the second one we have only 1 digit after it. So this has only 2 digits, and this has 1 digit after the decimal point. The rule says the result must have the least number of digits. Find the least number of digits among the additives. It is only 1. And your result must have only 1 digit after the decimal point. So you have to get rounding. Okay, so putting the result as 70.74 is not proper. If you have one of your measurements, you can only sure about 1 digit after the decimal point. So putting this number over here, since you're not sure what this second digit after the decimal point for this measurement, so you're not sure about this, there is no way you can be sure about this one, right? That means you just get rid of this one. Well, since this is 4, while rounding this result, just get rid of 4, and this will not change, of course, the 7, the digit before 4. But if this were like 6, let's say, if this were like 6 or 5, in that case, while getting rid of this 6, will increase 7 by 1. So it's proper rules for rounding the numbers off. Okay, so this is for this rule of adding measurement quantities by just looking at the number of digits after the decimal points. And this is how we did. This is how we did also for subtraction. For subtraction, we do the same. We use the same trick, the same rule. All right. So next, okay, suppose you want to just calculate the area that covered by this notebook, and the readings of your sides are just the same again. So area is just x times y, right? And let's calculate this. 29.4 multiply. Let me put this. 29.4, 41.34, and multiply this. So you just do this multiplication in your calculator, and your calculator, let me do it. Your calculator will give you the result 29.4 multiplied by 0.34. So the result is like 1215.396 centimeters squared, of course, because these are centimeters. Okay, so will you leave the result like this? 1215.30 and 396 centimeters squared. Of course not. We cannot leave the result like this because when you look at the number of digits or number of significant figures in your result, it's like 1, 7, 1, 2, 3, 4, 5, 6, 7. But you get this result by multiplying two measured quantities which has 3 significant figures in the first one and 4 significant figures in the second one. Okay? So how come that your result might be having a larger number of significant figures than the numbers of significant figures among your additives? Among your multiplicants. I mean, this literally means that okay, you're just doing some operation with some precision of your measurements, but you get a result which is more precise than the measurements itself. It's not logical, of course, because this is in something, it's a number that states to you that it is more precise than these numbers. So there is no way to have a result which is more precise than the measured quantities. So what the rule says is that, again, just look at the multiplicants and find the least number of significant figures. In the addition, it was like find the least number of digits after the decimal point. But over here, find the least number of significant figures among these multiplicants, which is 3, right? So your result must have the same number of significant figures with that of the least number of significant figures, 3. So this must be rounding off until it has only 3 significant figures. So how do you do it? How do you do it? Well, you can, look at this 1215 point something. This point something is something like 396, but it's like less than 500. So just get rid of these 1215 point. Well, it's still, you have 4 significant figures over here. How do you get rid of this 5? Well, this 5 can be get rid of just 0 and increasing this by 1. So 1220. But still, reporting this as an exact number is ambiguous because, it's not sure whether we take this last digit as significant or not. Let's convert this to a scientific notation, 1.22 times 10 to 3, right? Well, this way we are sure that, okay, only we have 3 digits over here, so the result must be having 3 significant figures because of this rule. So centimeters squared, that's it. This is the way we do it, okay? Don't leave your result as an exact number because, finding the number of significant figures in an exact number is ambiguous. So just can convert it to a scientific notation. Okay, so this is the rule. Also, the rule is the same for division. For example, if you want to divide 41.34 by, let's say, 29.4, whatever, you can do this division in your calculator, whatever the result is, the result again must be having only 3 significant figures. So you have to round this off to 3 significant figures. Okay. So that's about the rules doing some operations with significant figures, finding the result, how many significant figures. So these are the rules. What about delta A over here? Okay, so you know what the delta X is, we know what the delta Y is, but if this is a multiplication, are you going to use the same formula with that of addition X plus Y? This one? No. It is not the same formula. The formula is finding the error in your result if your result is just using as multiplication or division of the measured quantities. This is going to be equal, well, you are going to use this formula. In the formula, again, you have a square root, and in square root you have a summation, but this time your summation are not summing the absolute errors, but the relative errors. You're going to be summing delta x over x squared with delta y squared. And just take the squares of relative errors, add them, take the square root, and multiply this x times y, because your calculated value is x times y. Well, what if your result is not area but something like x divided by y? If you are calculating x divided by y, but what about delta a? Well, delta a is going to be just whatever this a is, put over here, x divided by y. Don't ever change whatever you see inside the square. This stays exactly the same. So addition of these relative errors stays the same. If this could be x times y or x divided by y, doesn't change at all the squared part. It only changed the factor in front of the squared part. Well, of course, the factor, if you're calculating x by x divided by, the factor comes x divided by y. If you're calculating x times y, the factor becomes x times y. Okay? All right. So I hope this is clear, but one important thing is that what if you have x, y squared, right? If you have x times y squared, if your multiplications terms has some power in it, in our case y is having power too. The only difference is that, okay, of course, always you modify the factor part. The factor part is always a. And you modify this by x times y squared, and your squared part will be modified also. The only thing is that since this power part is in only y, you just bring this factor to power 2 as a factor in front of your relative error in y. Delta y divided by 1 by multiplied by 2. Whatever the factor over here to power, you just bring this over a factor over here and take the square of all this 2 times delta y divided by y altogether. So if this were like 3, that means this will be 3. Whatever the power over here, it will be coming over here. Of course, if this is 3, of course you have to modify also this as 3. If this is, for example, 1 over 2, or let's say x multiplied by square root y, this is going to modify over this x times square root y. And what about over here? Well, since square root y means that y to the power 1/2, you just multiply this by 1 over 2. Okay? This is how we do it. Alright. Well, what about x divided by square root 2? X divided by square root y, sorry. Well, of course, you modify this like just whatever the a is, x divided by square root y. But this will not change 1 over 2. I mean, x divided by square root y simply means that x times y to the minus 1/2. But if your power has a minus sign over here, it doesn't change the factor. Factor always comes as plus 1 over 2. If it is minus or plus, it doesn't make any difference. It's always whatever the factor is over here in the power. The factor, just put the factor over here without any sign. Okay. All right. So, hope this is understood. And this is how we propagate for errors, for calculated results if you're using multiplication or division with your measuring quantities. So now let's come back to our original area calculation. So by using these numbers, let's do our proper calculation as an example. Okay. So let's do this in the calculator. Multiply. What was the result? Okay. The result was 1.22 times 10 to the power 3. All right. So what about the this calculation of error? Well, when you look at this relative error delta y over y, where delta y is 0.01, which is 10 times smaller than delta x. Also, y value y over here is larger than x value over here. You will see that this part is going to be much, much smaller than this part. So addition of this will not change. And in addition to the 1/10 of this, you also take the square of it. So this will affect more, only 100% of this value. So this will not have any effect. And adding this relative error to this one will not change abruptly this term inside the square bracket. So you can simply take this as the square root as square root of the relative error of x squared, but since this is square over here, it's just delta x over x. Delta x over x. So let's calculate, after this simplification, calculate this. X times y was just, do all calculations without rounding every term off first. Don't do this. Whatever the numbers over here, just use exact numbers. 29.4 over here, 41.34 over here, and put all these numbers over here and calculate in your calculator and put the result, and then whatever you have to do as rounding off, do this rounding off as after you use all exact numbers and put find the result and do your rounding off after that. Don't round while putting these numbers over here. Don't round off x while you are putting over here y over here. Don't do that. Use all the exact numbers over here and find the result, and then you have to do the rounding off. Okay, so I will just calculate this. So when I just calculated this, putting these all relevant numbers over here, which I find this result 5.134. And now, how can we put this next to a? Well, since we have to report this a plus minus delta a, 1.22. So we have to also write this error part as power of 10, the same power, and this is going to be like 0. If we multiply this, divide this by 1000, 0.005134 times 10 to the power 3. Well, one thing that I stated over is very important is that this way of writing this number 5.134 as power of 10 is not a proper scientific notation. We're not taking care of the rule of writing down the scientific notation over here. We're only just trying to match up the power of 10 for the error part to the power of 10 for the measuring part. Because the power of 10 is the measuring part is 10 to the power 3. That's why we need to write down this result as power of 3, 10 to the power of 3. So is that right? 1, 2, 3. Yes, this is right. So this is plus minus 0.005. But the thing is, well, we cannot keep all these digits. What was the rule in recording the error next to the measurement part is we have to match up the number of digits after the decimal point. After the decimal point, we have only 2 digits. Over here, after the decimal point, we have 1, 2, 3, 4 digits, 4 and more, 4, 5, 6, 7. So since this is a number which is larger than 5,000, the getting rid of all these make this 0 increase by 1. So we just increase this by 1 and times 10 to the power 3. Okay, centimeters squared, of course. So this is how we write down the result of calculating the area for these two side measures of x and y, and also together with its error value as an example. Okay, so if taking these errors and calculating by using the relevant formula, etc., leads us to write down the result like this. I hope this is understood, and of course there are many examples of dealing with these propagation of errors using these rules of significant figures and also rules of calculating the error. Just check them all in other videos in my playlist on or the YouTube channel, just to study more. Okay, that's it.